Alright, I'm pretty excited for this video because in this one we will be implementing YOLOv3 completely from scratch. So what do you need to be able to follow this video? Well, preferably you have some understanding of how the original YOLO algorithm works, and I have a completely separate video on that actually, and you could just watch the initial 10 minutes of that video if you're completely new to YOLO. But in this video, I will also start with a quick recap of how YOLO works, and then go and discuss what the main differences between the original YOLO and YOLOv3 are. And then we will implement it from scratch in Pytorch. All right, let's get started. So let's get started with a quick recap of the original YOLO and then the differences between YOLO and YOLOv3. And lastly, we'll implement it. But so one thing I forgot to mention is that there will also be pre-trained weights of this model that I've trained on Pascal VOC, and I'm trying to train it on the MSCOCO dataset as well, but it's such a large dataset, so it's taking a while. But when that is done, I will upload it to GitHub also. Alright, so a recap of YOLO. So the idea is in object detection is that we have objects, and we want to detect a bounding box for those objects. So in this case, we want to output two bounding boxes, right, around perhaps like this. Probably I'll put a better bounding box than that. But you want to output a bounding box, and you want to say which is the object. So in this case, it's a dog, and you also want to do the same thing for the right one. So without going into too much detail, there are many different approaches for solving this problem. And the way that YOLO solves it, that was sort of revolutionary, is that we do it in a single forward pass. And the way that we do it is that we split the original image into a grid. So in this case, if we split it into a 3x3 grid, it will look something like this. And then the idea is that for each cell, we will make a bounding box prediction. All right, so if we go back, then it might be a bit tricky, because if we just look at, for example, the right dog, so let's see, the right dog right here, we have sort of a 6 different cells that the dog is in, and similarly for the left dog. So how YOLO solves this is that we look at the midpoint for each object. So if we do that, then perhaps the midpoint is somewhere around here. And the idea is then that only those specific cells will be responsible for outputting that there's a dog there. So in this case, the one in the center, this one will be responsible for outputting the right dog, and then this to the most left will output that there's a dog, the left dog. All right, so everything is sort of relative to the cell in YOLO. So if we zoom in on the leftmost cell, then it would look something like this, where again, everything is relative to the cell. So in the top left, we have 0, 0, bottom right, we have 1, 1. And so if we just imagine that what we want to do now is we want to output a bounding box for this object in this one. So each bounding box will have 4 values. We will have an X value, Y value, and a width and a height. We will also have some more for the class prediction and so on, but we'll get to that in a second. Just to be able to create a bounding box, you need 4 values. And so if we step through one of those at a time, the X value will be between 0 and 1, right? So I think the X value is across this axis actually. And so it will be between 0 and 1 because we have zoomed in on a cell that is responsible for the output. So we're sort of assuming that there's an object here. So it will be in the center right here, perhaps, maybe 0.5 then. And similarly for the Y value, it will also be between 0 and 1. Now for the width, this can actually be greater than 1, and that is the case if the object is wider than an entire cell. And so similarly for the height, it can also be greater than 1 if the object is taller than an entire cell. So, if we just zoom out again and look at the entire image, we can see that the height of both of those two dogs are greater than an entire cell. So maybe, maybe this one height is maybe 1.5 times 1 cell height. So as I mentioned, in addition to the X, Y, width, and height, each box will also have a prediction, have a probability rather, that there exists an object in the cell. So if we didn't have that, then every single cell would sort of output a bounding box and everything would look super messy. So we have to also train the network to say, for each cell to be able to say, here's an object, take my bounding box. Or here's not an object, don't take this bounding box. And addition, we also want to know sort of when we output a bounding box, we want to know what is in that bounding box. So in this case, it's a dog, it's a cat, and so on. So we're also going to have class predictions, and I think we'll get to those in more detail when we actually implement it. So that's sort of a quick recap of YOLO. And again, I've made another video where I go into a little bit more depth, so you can watch that video if you're still confused over the original YOLO. So then, the interesting part, what's new in YOLOv3? So sort of the major difference, I would say, is in the architecture. So the original YOLO outputted a single grid of 7 by 7. What's new, and we'll sort of ignore, sort of ignore everything at the top here for now, and let's just focus on these three right here. So as I said, the original YOLO outputted a single 7 by 7 grid, and what they found was that was great for large bounding boxes, but it wasn't so great for small bounding boxes. So the idea here is, I guess, let's just try on different scales, different cell sizes, and the model itself can learn what's useful, I guess. So for the first one, the idea is kind of that here we can make it into a smaller grid size. So it's 13 by 13 grid size, and the idea is that here it can output large bounding boxes. So for the middle one, we have some more cells in the 26 by 26 grid, and that is good for sort of medium-sized objects. And in the last one right here, we have a lot of different cells, so that's great for smaller objects. So that's sort of the idea, is that we will run it through the CNN, and now they use a bunch of tricks like ResNet, skip connections, and other tricks right here that are sort of ResNet-like, in that it uses concatenation of the channels, sort of similar to ResNet, but instead of addition, so here they use addition, here they use concatenation of the channels. So they use a slightly different architecture now, but they run it through some COM layers, and then we get to sort of a scale prediction, and we run it through some COM layers right here, and we output this, which is a 13 by 13 grid size. After that, we upsample it using bilinear, so that's the green one right there. We run it through some other COM layers, and then we do another scale prediction. So let me write exactly. So here it's 13 by 13. Here is going to be 26 by 26, and then here it's going to be 52 by 52. And yeah, so one thing also is that the original YOLO outputted a single bounding box for each cell, which sort of made it so there could only be one object per cell. But now in YOLOv3, and I think this was also in YOLOv2, we're sort of skipping YOLOv2, but in YOLOv3, we output 3 different bounding boxes for each cell. So a lot more predictions. And when you take into account that we now use 3 different scales for our predictions, it just leads to a massive amount of bounding box predictions. And in fact, I think there's so in the original 7 by 7, so that would be 49 different. In this one, we have over 10,000 different bounding boxes. So it's a lot more predictions, but it's still pretty fast, which is kind of what YOLO was sort of made famous for, I guess. Was that it was also very, very fast. So a new thing that was also in YOLOv3 is the introduction of anchor boxes. And this was actually also in YOLOv2, but again, we're skipping that one. So yeah, anyways. So anchor boxes is a way for us to sort of encode previous knowledge into the model. So, which is, you can discuss if that's a good thing or not. But the idea is that maybe we have one box for vertical object and we have one for horizontal object. So instead for the model to come up with a completely new sort of a bounding box, we say that, here you have one anchor box. Could you slightly adjust this anchor box to fit the object in the image? So you can imagine that that's much easier to just adjust an anchor box than to find a complete one from scratch, so to speak. So what they did in the original YOLO, if we go back, is that we had, so as I mentioned, we have 3 different cells for each. So we have 3 anchor boxes for each cell, and we have similarly for 3 different anchor boxes per cell for scale 2 predictions and the scale 3 predictions. So in total we have 9 different anchor boxes, where the idea is that the first scale will have larger anchor boxes, making it easier to detect larger objects. The scale 2 will have sort of medium-sized anchor boxes, and scale 3 will have the smallest anchor boxes. So then you might be like, well, how do we find those anchor boxes? That's sort of a tricky thing to say. I mean, you wouldn't just do this, right? You wouldn't just take one vertical and one horizontal. So what they did in the YOLOv3 paper is that they used a smart way of doing k-means clustering, where they used the loss function was to sort of maximize the IOU with all the target bounding boxes. So that's how they did it. We're not going to go through that. We're just going to take the anchor boxes that he used, that he found in the paper. All right, so we have those anchor boxes. We know that we have these previous encoded knowledge in the anchor boxes. So how do we actually produce our predictions? So the anchor boxes, sort of the formula, is that we have an output. So let's just start with bx. That's the x midpoint, which is relative to the cell again. So we have this, which is output from the model. Then we take a sigmoid of that, which means that it's guaranteed to be between 0 and 1, right? Which is exactly what we want. And then for the y1, we have similar thing, where ty is sort of just a float value coming out from the model, and then we take a sigmoid of that and making it between 0 and 1. For the width, we have tw, which is output float value from the model, and then we take the exponent, we take the tw exponent of that value. So whenever I see that, I'm sort of worried, because that sort of taking exponent makes it quite unstable, I would say. So I'm not exactly sure why he used exponent here, but I guess, he experimentally were able to find that made it work better. But additionally, I guess this also makes sure that everything is positive, which is a good thing for the bounding boxes. So yeah, and the way that we encode sort of the anchor boxes, so every anchor box has a width and a height. So how we produce the new width is that we take this value, right, this value, and we multiply it with pw, which is the sort of the encoded knowledge of that particular anchor box width. So this is anchor width. And then similar thing for the height, where we have th coming out from the model. We take the exponent of that, and then we multiply that with the sort of the anchor box height that we have. All right, so that was sort of a summary of the major differences. There might be some small ones, and I'll mention those as we go through the implementation. But anyways, let's implement this now to understand all of the details. All right, so this is going to be split into some different parts, and I want to start with going through the model implementation. Then we're going to go through dataset loading, and then loss function, train function, and yeah, that's pretty much it. So let's start with the the model. All right, So one thing also is later on for the dataset and all that, everything is going to be in the description if there's anything you need. But so for the model anyways, we're just going to use two imports, import torch and import torch.nn as nn. So that's pretty much it. And what I've done also for the model is that I've written down sort of a config file. So in the original, sort of in the paper, they didn't actually mention how exactly the model looks like. So YOLOv3 was more like a tech report. That's what he said in the paper anyways. So you had to sort of go through the source code a little bit. So what I did is that I went through this entire config file, which is written in darknet, so it's not Pytorch. And I was able to find some patterns and write down a config file of how this architecture looks like. So if we go back, I'm actually just going to copy paste in that config file. So I'm going to paste that in. That's how the model looks like. All right. So it might be a little bit, you might be able to clean this up even further, but this is what sort of the main part is. So, all right. So what I've done here is that pretty much if we have a tuple, right? So this one, for example, then this is going to be the out channels, the kernel size, and the stride. All right. So every convolution in YOLOv3 uses same padding. So we don't have to write up the padding. Pretty much it's always going to be 3x3 kernel size, pretty much. But so this is the out channels from that conv layer. That's the kernel size, and then we have the stride. So I guess in this case we have, we have 3 as in channels, and then we have 32 out, kernel size 3, and stride 2. Then we have 64, 3, and then 2. All right, and then for a list we have sort of, I guess it's sort of unnecessary, but I wrote B for block and then the number of repeats. So it used these sort of residual connections, and I guess we can bring out the paper to just watch that. So he had some parts written down in the paper. So for example, here he used these 2 convolutions, right? That's what we wrote up in the beginning. Then he used these residual blocks, and this is the number of repeats of those blocks. So we had 1, 2, 8, 8, 4. And this is called darknet 53. And he actually pre-trained this part of the network on ImageNet, and then he added additional layers for YOLOv3. So we'll get to that. But anyways, that's for the block right here. So these are sort of residual blocks, where the thing right there is the number of repeats. So yeah, so this is B, and this is the number of repeats. So that's it. So all of these up to that point is exactly what we just saw. That's darknet 53. And then he added additional ones, additional layers. So he used here, this is just out channels 502, kernel 1, stride 1, 1024, kernel 3, stride 1. And then I wrote S. And this is where sort of that branch that we saw. So I should bring up this image as well. So S right here is actually this right there, this sort of this branch. Now it's not exactly as the image here. There's only 2 convolutions here, and then it's a scale prediction. So the image is a little bit off. But anyways, that's what you can imagine, where we write S, we do the scale prediction. And then in between we have 1 conv layer, then we have an upsampling. 2 conv layers, and then we have another scale prediction. 1 conv layer, another upsampling. So right, this is for the scale 1, then we upsample to 26 by 26. Then we don't downsample anything, so we use same convolution everywhere. And so we upsample it to 26, 26, then we do another scale prediction right there. And then we upsample it again, and lastly we do another scale prediction. So that's the config file. And I'll copy paste in, let's see, I wrote some information about the config file here. So, tuple is filters, kernel size, stride. Every conv is the same conv. List is structured by B indicating a residual block, followed by the number of repeats. S is for the scale prediction block. And then we also compute the YOLO loss on that particular one. So that's the branch downwards in the image. And then U for upsampling. All right, so you don't have to understand the detail. It's sort of arbitrary, right? You just need to understand sort of the structure. All right, so I guess what we can do now is let me just write down the structure of the implementations that we're going to use, sort of the classes. So we're going to have a CNN block, which is going to inherit from an module like that. And then we'll have pass, and we're also going to have this residual block that we talked about, right? That's for the list right here. So that's for the B. So we're going to have that. Then we're also going to have a class for the scale prediction, and that's for S, right? That's the branch. So other than that, those are sort of the three essential ones. Then we're going to have, I guess, YOLOv3. So in YOLOv3, this is where we're actually going to put everything together. So we're going to be using the config file in YOLOv3 by utilizing these different blocks and scale predictions, create the model, and then do the forward pass. But before we get ahead of ourselves, let's just create the com block. So we're going to have an init layer, and the init layer is going to take some in channels, some out channels. What else? So we're going to have, so one thing we're going to have also here is bn act, is what I called it. We're going to set this to true by default, and this is indicating if the block is going to be using batch norm and an activation function. And then we're going to have quargs as well. So we're going to have self.conv is and then conv2d of just in channels, out channels, we're gonna set bias equals to not bn act. So if we do use bn batch norm and activation function in the block, then we want to not use a bias, right? If we use batch norm, then bias is a unnecessary parameter. So that's why I'm writing not bn act here. A little bit confusing, perhaps. You could probably restructure this. And then we're going to send in the quargs, which would be the kernel size and the stride. Yeah. All right. And I guess the padding as well. So then we're going to have self.batchnorm is batchnorm2d of out channels. And then what he used for the activation function was leaky relu. So leaky relu of 0.1 in the stride. Other than that, we'll just do self.use bn activation. We'll just set that. All right, so now in the forward, we're going to check if self.use bn activation, then we're going to run it then we're going to run it through all of the ones. So self.leaky of self.batchnorm of self.conv. And otherwise, we're just going to return self.conv of x. And there are probably some of you that are like, why is he doing it that way? There are probably better ways to do it. But yeah, if you find a better one, I'm happy to change it. So, the thing that might be unnecessary is the if statement in the forward pass. That might, we might lose on some performance, but I think it's pretty negligible, I would imagine. I haven't tested it though. So we're going to call this super, just to inherit from NN module. And that's pretty much it for our CNN block. And sort of the reason why I did it with this bn activation is that for our scale prediction, right, that's going to be in our output. Then we don't want to use batch norm and leaky relu on our output. So in our scale prediction, we're going to be using CNN block, but we're going to set it to not use batch norm and activation. And that's what we do right there. I guess one thing you could do is you could just create sort of a com block inside scale prediction, and in that way you could ignore these ugly and if statements and stuff. So for the residual block, we're gonna create our init. We're gonna send in channels. We're gonna send in use residual equals true, and then num repeats is 1. And then we'll call this super of init. So the reason here why I'm specifying the use residual is because in some cases we're going to be using the skip connection, and in some cases, in just going through the config file of YOLOv3, he didn't use the residual. I don't know why, but he didn't, so we'll just replicate it as he did it. And then for the number of repeats, we're going to set it to 1 as default, but that is something that's going to be sent in, which is indicated by this right here. So that's number of repeats equal to 8. All right, so we'll do self.layers. It's going to be a module list, right? And here we're going to store it because we're going to have a lot of repeats. So we're going to for repeat in num repeat. So in if the number of times we are going to repeat it, we're going to be adding self.layers plus equals, and we're going to add CNN block of channels. And then how he did it in the residual block is that he simply divided by channels by 2, integer by 2, and then he used a kernel size of 1, and then the padding should be 0, which it is by default. And then we'll have CNN block again, 2 channels divided by 2, 2 channels, and then we'll have kernel size 3 and padding of 1. So a same convolution. So the only thing this really does is it downsamples the number of filters and it reduces the number of filters and then brings it back again. So that's all that does. And then what we'll keep track of as well is if we're going to use the residual, which is use residual, and self.num repeats is num repeats. And we'll get into exactly why we need to store this. But yeah, I'll just keep it there for now. And then in the forward part, we're going to send in some image X, right? So forward of X, similarly as we did up here. Then we're going to do for layer in self.layers. And we're going to check if we use residual on this, then we want to do X. It's going to be a layer of X, right? So we've run it through this com block. Remember, we didn't change anything, right? It's same padding, and we didn't change the number of channels. So if we want to use a residual, we're just going to add X after we run it through those com layers, 2 com layers. But if we don't want to use a residual, we're just going to do a layer of X. And I guess maybe you could use this on a single line. Maybe X is layer of X plus X if self.use residual else layer of X. Maybe that's a little bit cleaner, like that. And then in the end, after running through all of those, we're just going to return X. And that is pretty much it for that. And I guess we can just do underscore. All right, so hopefully you're following so far. We've just used a com block and we used a residual block. Now for the actual scale prediction, what we're going to do here is we're going to create our init. And here we're going to be sending in the in channels and the number of classes that we have. So here is actually where our output is going to be. So we'll first call this super, and then we'll do self.prediction is and sequential of CNN block of in channels. And then let's see here. So how he structured it in the config file is that he took in channel, he then multiplied in channels by 2 with a kernel size of 3, padding equals 1. And then for the second one, he used CNN block of 2 times in channels, and then he brought it down to num classes plus 5 times 3. And then BN activation is going to be false. Kernel size is going to be 1 here. So let's see if I did anything correct. Okay, this looked good. So the reason why we're doing it this way, all right, is because for each anchor, right, and we have 3 anchors for every single one, for every single cell, we have 3 anchor boxes. For every anchor box, we need to have 1 node for each of the classes that we want to predict, right? That's just normal you're used to that, right? For ImageNet, we have 1,000 nodes for 1,000 classes. Then we have +5, and the +5 here is because we want to output the bounding box. So each bounding box is going to have a probability, let's call it PO maybe. So probability that there is an object in that cell. Then we want to have X, Y, width, height. Okay, so that's 5 values, and that's why we get this value right here for the output. And then we'll do self.num classes equals num classes. And in the forward part, so in the forward, we're going to be sending in X. And what we're going to do is we're just going to return self.prediction of X. Then we want to reshape that that we send in through this last com block. What we want to reshape it to is sort of the number of batches, sort of number of examples in our batch. Then we want to do 3, and then self.num classes times 5. Plus 5. And then x.shape of 2, x.shape of 3. So what we're doing here is that we're just sort of making this into 2 different dimensions instead. So instead of having a long vector of all the bounding boxes, it makes more sense, I think, to split it. So maybe this would be more accurate or make more sense. So with 3 times that, and then we're just splitting it right there. Yeah, one thing I also did is that I didn't want, I didn't want this to be in that dimension. So I also did .permute. So we want to keep the examples the same, want to keep the anchors the same, but we don't want to keep this, we don't want to keep that the same. So we want to put this at the end. And the way we do that is we say that this right here should be on this location, and then this right here should be on this location. So this is 0, 1, 2, 3, right? The third one should be, I guess, on the second one. This is kind of, I don't know how to explain this. So this is anyways the third one, which comes from, it should be second, which is the third dimension. And then this one is the fourth one, and then the one we want to have at the end is the second one. So 0, 1, 2. We want to have that at the last position. So I guess let's bring an example. So we have n examples in our batch. Each example has 3 anchors. Each anchor is going to have, let's say we're just doing it for the scale 1 prediction, is going to have a 13 by 13 grid, and every one of those 13 by 13 grids is going to have 5 plus num classes output. And if you would change it to scale 2, this would be 26 by 26. If you would change it to scale 3, it would be 52 by 52. And if you would change the number of anchors that you want to use, you would change this to maybe, let's say, 5 anchors. All right, so hopefully you're with me with the scale prediction. Now what we want to do is we just want to put it all together. So we're going to do define init of inChannels equals 3, num classes equals, let's put it to 80. So 80 is what MSCOCO used. So maybe we don't want to use that as a default. Let's use Pascal VOC, which is going to be 20 classes. Starting with calling super, and then just specifying number of classes is num classes. Self.inChannels is going to be equal inChannels. And what we want to do now is we want to create all the layers. So self.layers is self.createConv layers. So we want to create that function, right? We're going to have a forward. In the forward, we're going to do that later. But what we want to do now is create conv layers. So here is where we're going to create all the conv layers using the config file. So pretty much we want to keep track of all our layers in not in a list. Then it won't be tracked by Pytorch. So if you're doing model.eval and toggling all of that, so you want to use a module list. Yeah, so we want to do inChannels is self.inChannels. Now what we want to do is we're going to go through the config. So for module in config, then we want to check, if we scroll up, we want to check, is this a tuple, or is it a list, or is it a string, right? Those are the three different types right there. So if it's let's start, if is instance module, if it's a tuple, then it's pretty simple. We just want to do a convolution, a com block, CNN block. So we want to take out from that module, we're going to have out channels, kernel size, and the stride from module. So we'll take those out, and then we'll do layers.append CNN block, and we're going to send in the in channels, the out channels, kernel size is kernel size, stride is stride, and then we're also going to specify the padding, which is going to be 1 if kernel size equals 3, else 0, right? So that's pretty much it. Let's just restructure this a little bit like that. So we have layers.append CNN block, and that's pretty much it. And then we close that layers.append, and what we want to do now is we need to set in channels to out channels, right? So the in channels for the next block is going to be equal to the out channels of this block. All right, if it's not a tuple, we can check else if is instance module, if the module is a list. If that's the case, we want to take out the number of repeats, which is going to be module of 1, right? That's the second value of the list. Just to be clear here, what we've gone through now is the tuple. Now we're going through the block right here, or the list, which has a string, which doesn't tell us anything, just to make it clear for ourselves. But then the second value here is the integer for the number of repeats. So scrolling down again, we want to do layers.append residual block of in channels, and then num repeats equals num repeats. Pretty simple. So that's it. Otherwise, we want to check, and here it will be a little bit more tricky, but if it's a string, and if the module is equal to s, right? Because we have scale prediction and we have upsampling. But if it is s, then we want to plus equals, so we want to add. When I go through this, I'm not exactly sure why I did it this way. There's probably a good reason for it. Maybe it was just to make things more compact. Why I didn't just include this part in the scale prediction. Anyways, what I did is that when we have a scale prediction, we have sort of the same behavior every time. And the behavior that we have is that we use a residual block, the same sort of a pattern, but we don't use the residual. So we use residual to false, and the number of repeats that we do there is 1. After that, we do a com block with in channels, and then we take it to in channels division by 2, and kernel size is going to be 1. What we do then is we do the scale prediction, taking as input in channels divided by 1, and we set the num classes equals self.num classes. Anyways, if that's the scale prediction, this is the behavior that we have. How I got to that was just reading the config file, seeing when we have an output, how does the behavior look just before that. Anyway, so else if the module is an upsample, we're just gonna layers.append and an upsample. Scale factor is going to be 2, so we want to upsample by 2. I think you can also set that you want to use nearest or bilinear. I think it's nearest by default, but I'm not sure about that. After that, we're going to set in channels to in channels times 3. And you might be like, why are we doing that? And the reason for that is because just when we have an upsampling layer, that's also exactly where we want to concatenate. So bringing up the image right here. And again, the image is definitely not perfect because here, how I found it at least, is that we should concatenate just after the upsample, right? So this right here should just be directly after the upsampling layer. There shouldn't be any conv layers in between here. So that's what I think at least. So yeah, so that's when we do upsample, that's also when we want to concatenate. And yeah, one additional thing is that we want to concatenate the one that was added last. So we sort of add this to a list where we keep track of the output from this one and keep track of the output from this one. And then when we get to this point, right, just after the upsampling, we want to take the one that was outputted over there and we want to concatenate it. And when we do that, we obviously get more channels because we concatenated channels from previously. And specifically, we have in channels times 3. All right, so this is definitely a little bit messy. I think that's just the way it is. But I've tried to make it as clean as I possibly can. And there are probably some things you can do to make it even better. But after all of those stuff, we've created all the layers that we want. So we're just going to return the layers. Now we've created that part. The only part that's left now, and sort of creating the model is one of the most difficult parts. But in the forward part now, we're going to keep track of outputs, right? Because we have one output for each scale prediction. We're also going to keep track of the root connections. And those are exactly that I just showed you with the where we concatenate the layers. Concatenate the channels. Those are sort of the skip connections for concatenation. Other than that, we're just going to do for layer in self.layers, and we're going to check. First, we're going to check if this instance layer is a scale prediction. So when it's a scale prediction, we want to output.append layer of x. But now, because we have this branch, we want to continue from where we were previously, right? So we want to do this prediction, we want to add it to outputs, but then we want to go back. So one way I found to do this is if it's a scaled prediction, we're going to add that layer, and then we're just going to continue. So we're sort of, I guess, skipping. We're not going to continue from this place. We're going to continue from this place where we were from the beginning. So if it's a scaled prediction, we'll just add it and then continue. Otherwise, we're going to set x is layer of x. And then we'll check if it's a residual block. And the layer.num repeats is equal to 8. If that is the case, and that's what I found from the config file, is that that's where we want to add these roots. Okay, so if that's the case, we want to do root connections dot append x. So that's it. After running it through those, we want to add it to the root connection. All right, so if it's not, else if is instance layer and then upsample, then we want to first concatenate x and then root connections -1. And then we want to concatenate along dimension 1 for the channels. So that's sort of the behavior that we talked about before, is that if we're using the upsample, that's where we want to concatenate with the last root connection, with the last one that we added. So what we do then is we just do root connections dot pop. So we remove the last one. And in the end, we're just going to return outputs. And that is it. Yeah, all right, so that's the model. What we want to do, obviously, is I'm just going to copy paste in a test right here. So if name is main, we're going to set num classes to 20, image size is 416. Maybe this is a part that I didn't mention. So in YOLOv1, image size was 448. In YOLOv3, it's 416, but it also varies. So he used multi-scale training, meaning he also used different sizes essentially. But 416 was the main one. So moving on with our test file right here, we do our model, which is YOLOv3 of num classes equals num classes. We use some random output input as 2 examples, 3 channels, image size. Then we do out of modulo x. And then what we're doing here, and I guess this is sort of a bit confusing perhaps, we just want to assert that the first one is of shape, 2, and then 3 anchors, and then 13 by 13, and then num classes plus 5. But the general the general structure or pattern is that we use the image size divided by 32, because that's the stride that we've divided by. And yeah, so that's the general structure if you want to change the image size. So we just want to assert that those are the shapes, and if they are, it's a success. So let us run this, and hopefully we haven't made any errors. We probably have. Yeah, so num repeats somewhere, that is in the residual. So here we want to do for, yes, range of num repeats. All right, there's another error. Yeah, all right, so self-leaky of self-bash norm of self-conv of x. Let's see if it works now. No. All right, yeah, so I think the error right here is that in the conv block here, we need to run through both of those. Yeah, so I missed that part. This should be an NN sequential, and that should be inside the NN sequential, like that. So a single layer here is has these two conv blocks, and in that way I think we can do the addition, but it still doesn't work. So yeah, all right, yeah, so I think I found the other error, which is that after we do this, we want to continue from this block, right? So the scale prediction is the branch, and that's sort of one output, and then we're continuing from this branch. But here we change the number of channels, so we want to set in channels equals in channels divided by 2. And yeah, I mean, hopefully this works now, but there's sort of a, you oftentimes get these errors and you sort of just have to debug what's wrong. And now I'm printing all the time as well, so yeah, let's remove that print statement. But yeah, as we can see, it now works on the test case, and that means that it's probably working. What you would probably want to do is make sure that it can just overfit some, well, we're going to do that later on anyways, but you would probably want it to overfit some random noise just to make sure that there's not something major wrong in the model. But this should be correct now. So that was the model. It's about, let's see, 150 lines of code. And what we want to move on to now is the data set. All right, so now that we've done the model, we're going to move on and we're going to do the data set. And what I want to show you as well is the structure of the data set. So you won't have to do any modification. So I'm going to upload all of this to Kaggle, and there's going to be a link in the description if you want to use Pascal VOC, for example. So there's a folder. We have the images, so 43,000 of them. We have the labels for each of those. So let me just open one of them. So what we have here is the class label for a bounding box, and then we have X, Y, width, height. And so we have, perhaps in some images, we have multiple bounding boxes. So those are all in separate text files. And then what I've done is that we have a train CSV and a test CSV. Yeah, which basically says this is the image and this is the text file label associated with that image. Similarly for the test CSV, and then I have two additional ones where the purpose of those are just to overfit a single example, so 8 examples and 100 examples, just to make sure that the model works. The second data set is the MSCOCO, which is structured in a very similar way. We have images, labels, test, and train CSV. Again, all of those will be in the description, uploaded on Kaggle. So yeah. All right, so let me just copy paste over the imports that we're going to use. So these are the ones that we're going to be using. I guess we can comment out this config, because those are going to be all the hyperparameters and stuff, but we haven't made that file yet. So we're going to use NumPy, OS, Pandas, Torch, Pill to load the image. We're going to be using Torch utils, the dataset and data loader, which I guess we don't need to do here, so we might not need that. And then we're going to use from utils, we're going to have IOU and null-max suppression. I don't think we need null-max suppression. Let's see. But anyways, the kind of so those are just basics. The utils file are gonna have some stuff, and I'm not going to cover that in depth, mostly because I've covered all of those things in separate tutorials. Like if you would want to know intersection over union, I have a separate video in the object detection playlist. Non-max suppression as well. There's mean average precision in that also. All of those I have separate videos for. This is sort of just focused on YOLO and getting that to work, sort of. Yeah, so I'm going to copy paste that over as well, the utils file. So let me just show you. So this is I'm going to copy paste that utils file, and if you're coding along, then there's going to be a link to GitHub. Just take the code, take the utils file, and don't worry about it. But if you want to know the details of it, you just know that there are separate videos for them. All right. So what we want to do as well is we got to do image file dot load truncated files is true. This is just so that we don't get any errors when loading the images. All right. So for the class, we're going to do class YOLO dataset. We're going to inherit from dataset, and did I just remove those? Maybe I just removed them. So from torch.utils.data, import dataset and data loader. So we're going to inherit from data loader, and this class is going to be used both for the MSCOCO and Pascal VOC. So for the init method, we're going to have, let's see here. So the init, we're going to have a CSV file. We're going to have an image directory. We're going to have a label directory. We're going to have anchors. So right, those are the anchors that we're going to use for different scales. I haven't written them down yet, but I'm going to show you later on. The image size is going to be 416 as default. S are the grid sizes, which are going to be 13, 26, 52 by default. Classes is going to be 20, and we're going to set transform to none to start with. All right, so now that we have those, we're going to do self.annotations. It's going to be pandas.read CSV of CSV file. So that's going to be the train CSV or the test CSV. We're going to do self.image directory. All right, image directory is image directory, and then the label directory as well. The transforms that we're going to use, self.s, so the grid sizes, and then we're going to do self.anchors, and we're going to convert that to a tensor. So we're going to do torch.tensor of anchors 0 plus anchors of 1 plus anchors of 2. And the reason why we're doing that is so that we put all of the anchors together, and what we're putting together are the ones for the different scales, right? So here for scale, the first scale we have 3 anchors, second we have 3 anchors, 3 anchors. So this is for all 3 scales. Num anchors is then just going to be self.anchors.shape of 0. Then the anchors that we have per scale is going to be num anchors. So per scale is self.num anchors integer division by 3. So we're assuming that we have specific set of scales, right? 3 scales, but you can change the number of anchors that you have. Self.c equals c, and then we're going to do ignore IOU threshold. So what they did in the paper is that, maybe I should explain this later on, but basically what they did in the paper is that we're going to set one anchor responsible for each cell in all of the different scales. But if there's another anchor that has a high IOU, also a high IOU with the same object, and if that IOU is greater than 0.5, then we want to ignore those predictions. So the idea here is that, all right, we're going to have for each cell, if there's an object, we're going to have one anchor responsible for outputting it. The one that's responsible is the one that has the highest IOU with the ground truth box. but perhaps there might be cases where there are several boxes in the same cell that are very good at predicting the same object. If the IOU is greater than 0.5, then we are going to ignore the prediction for that one. Okay, so we're going to define length. We're going to return length of self.annotations. All right, now for the get item, and this is going to be, so we're going to get index. The first thing we're going to do is we're going to get the label path. So ospath.join of self.label directory, and we're going to get from the CSV, so self.annotations.ilook, and then we're going to do index, comma 1. 1 is because it's at the second column. So that's where the text file sort of name is located. All right, so when we have the label path, we can load them, right? And we can do that by using np load txt. We can specify the file name, which is the label path. The limiter is going to be space in this case. And we also specify that the number of dimension is going to be 2, right? We're going to have a row for each bounding box, and each bounding box has 5 values associated with it. All right, so that's it. The second thing though, and the thing then we're going to do is toList. The only problem here is that we're going to be using for augmentation, right, to augment the bounding boxes and all of that stuff. We're going to be using the albumentations library, which you can if you haven't watched my video on albumentations, it's okay. But if you want some more in depth on how to use that one, you can check out that video. But what we want to do for that one is that they want the class label to be last in the bounding box. So, right, the text files right now is class xy with height. They want it to be xy with height and then class. So how we solve that in an efficient way is that we use np.roll of that numpy array. We're going to specify, let's see, so np.roll, we're going to do 4 rolls, act is equals 1. So in this way, we're just sort of putting all the bounding boxes at the same time on the correct position, so that we have classes at the end. And that's really all that's going on here. So now that we have that, we're going to get the image path. Image path is going to be ospath.join of the image directory, and then we got to do the same thing of self.annotations of index, comma 0. So it's just the first column instead. Then for loading it, we're going to do image.open of image path, and then we're going to convert it to make sure that it's in RGB. I think some are grayscale images, in Coco at least. So making sure that it's RGB. Then for using the albumentations, we need to also make sure that it's a numpy array. So that's all we're going to do. Then we want to check if we have some transforms. We're going to do augmentations is self.transform of image equals image, bounding boxes equals bounding boxes. And yeah, that's just albumentations, how it works. So you send in the image, you send in the bounding boxes. In that way, if you rotate the image, the bounding boxes are still going to be correct. If you do a horizontal flip, the bounding box will still be correct. And you can imagine that doing augmentations by hand or creating the functions yourself takes a lot of work. So using a library here is very useful. And unfortunately, you can't just use Torch Vision because from my understanding, they only support for classification. So that's why we're using albumentations here. All right, for the image, we take that out from the augmentations. The bounding boxes, we also take that out from that augmentations. All right, so now that all we've done is we've loaded the label, we've done a transformation, which we haven't written yet, but if we have a transformation, that's what we're going to do. For target, we're going to do torch.zeros of self.numanchors, divide integer division by 3, so that we have sort of the same number of anchors at each scale prediction. And we're assuming here that we have So we're assuming two things. We're assuming that we have 3 scale predictions, right, that we have in our model, and we're assuming that we have the same number at each scale. In our case, it's going to be 3 in this value because we have 9 anchors in total. Then we're going to do s, comma 6, and we're going to do that for s in self.s. All right, so what's the difference here? What have we done here? For each sort of target, we have the number of anchors. We have 3, comma, the grid size, so 13 by 13, for example, for the first scale. Then we have 6 values. And why we need to have 6 values is we need to have a probability that there is an object. So that's the probability of, probability of an object. And that's just going to be 0 or 1 for the target. Then we're going to have, we're going to have x, y, width, height, and class. So what the rest of the values are going to be x, y, width, height, class. So that's in total 6 values. So then we have the targets, and what we want to do now is we want to go through each of the boxes. So for books in bounding boxes, and we want to, so this is kind of a tricky thing, right? We have the targets for all the different scales, and we want to go through each of our bounding box in the image, and we want to assign which anchor should be responsible and which cell should be responsible for all the 3 different scales, right? So each of the 3 scales should do a prediction, and we need to assign which anchors should be responsible and at which particular cells. So how we assign which anchor is responsible is that we check which has the highest IOU. So for that, we need to calculate IOU. So IOU with the anchors is going to be IOU. We imported that from utils. And we're going to send in the box. We're just going to send in the height and the width here. And we're going to do self.anchors. So this function calculates the IOU just from the width and the height. So we calculate the IOUs for the particular box and all of the anchors. Right? And I guess, so those are 9 different ones in our case. So what we do then is we want to check which anchors were the best. So we do IOU anchors dot argsort descending equals true and dimension 0. So the first one is going to be the best anchor. So now we can also take out x, y, width, height, and class label from the box, right, that we loaded right here for boxing bounding boxes. And we also want to do now has anchor. So we're gonna make sure that each different scale, that there is an anchor for each of the 3 scales for each bounding box. So we're gonna do false and then times 3. So just I guess false, false, false. So this is making sure that each of these 3 are going to be true at the end, and we need to make sure that that makes sure that there's a bounding box anchor for each of the 3 scales that are responsible for predicting the particular object. Hopefully you're following. This might be a little bit tricky perhaps. All right, so what we want to do then is we want to go through for anchor for anchor index in anchor indices, right? So we're going through the best one first. Now what we want to do is what we want to do first is we need to check which anchor does this actually belong to, right? So we have 9 different ones. There are 3 associated with scale 1, 3 associated with scale 2, and 3 associated with scale 3. And those are all different anchor boxes. So how we check which scale it belongs to, scale index, we do anchor index divided by the self num anchors per scale. So perhaps this anchor index might be 8. Then we do divide by 3, which gives us 2. So it belongs to scale index 2, which is the last scale. So what this tells us, this is going to be, scale index is going to be 0, 1, or 2. This is going to tell us which target we need to take out from this list of targets that we have. So if it's 8, we're going to take out 2 because we want to take out the last anchor, which is associated with the 56 by 56 cell grid. So when we have that, we want to also make sure that we know which anchor on this particular scale are we assigning it to. So the anchor on this particular scale that we're looking at is going to be the anchor index and then modulus self.num anchors per scale. And so for example, so this is also going to be between 0, 1, or 2, but it's going to be dependent upon which scale we're looking at. So here we're computing which scale, here we're computing which anchor in that particular scale that we want to use. So yeah, each of the scales has 3 different ones. Which of the 3 do we want? Yeah, and then we're gonna get the grid size. So self.s of scale index. We're getting the how many cells there are in this particular scale that we're now looking at. And let's see. So what we want to compute is yeah. So one thing I forgot to mention is that the labels that we get is in the entire image. So let me bring that up again to be clear. So the labels that we get here are associated with the entire image. So this tells us it's 0.5 in the entire image, okay? And this is 0.5 in the entire image. So this is pretty much perfectly in the center. The midpoint is pretty much perfectly in the center in the entire image. So I guess perhaps that's the, yeah, right here. That might be the person, I think. But so that's from the entire image, but we want to specify it to a specific cell, because remember, everything in YOLO is relative to the cell. So how we do that, and we check which I and which J, so which cells are they associated with. We're gonna take int of s times y, and then int of s times x. So I is the which yeah, I guess is, yeah. So this I tells us which y cell, and j tells us which x cell. So you know, if we have 0.5 for, let's say x is 0.5, and let's say that s is 13, right? Then we get that it's in cell 6.5. If we take the integer of that, we get cell 6, right? So it's in cell 6 in the x coordinate, and similarly for the y one. So it's going to be, yeah, I hope you're following there. Yeah, so we're just taking out which cell. So the I and the j, then we're going to do which the anchor taken, right? So we're going to take out that from the scale index, and then we want to take out the specific anchor on this scale, right? So this is checking in this list here of the different target tensors. Here we're taking out which anchor on that particular scale, and then we're taking out the I and the j for the particular cells that we're looking at. So we're taking out I and j, and then we're taking out 0 for the probability that there is an object, and we're going yeah, we're just taking out that one because it might be the case that this anchor has already been taken by another object, which is, you know, super rare that you have 2 same objects with same bounding box. Yeah, I guess that would be pretty rare. But what we want to make sure is that we haven't taken this before. So we need to just check, if not anchor taken, and that we don't already have an anchor on this particular scale index for this box. Yeah, so we need to make sure that the anchor has not been taken and that we don't already have an anchor on this particular scale for this bounding box. So yeah, that's because we want to have 3 different, I want to have a prediction at each of the 3 scales. But if that's not the case, then we want to set targets of scale index. Then we want to take the anchor on this scale, I and j, element 0, and we're going to set that to 1. Now that remember that we want to set things relative to the cell. So I and j found which cell are we looking at. Now we want to find what is the x value in this cell. So this is going to be between 0 and 1. And how we do that is we take s times x and we subtract j. So j is associated with the x value. So for x, we take s times x minus j. So for example, if it's 6.5, we subtract 6, which gives us 0.5. So in the middle of this particular cell. And we'll do pretty much the same thing, s times y minus I for the y value. So here both are between 0 and 1. Okay, so the width for the cell and the height of the cell is going to be just the width times s and the height times s, right? If we have a width of 0.5, for example, that means that it's 0.5 of the entire image, right? So if s is 13 and the width is 0.5, then it should be a width of 6.5. So we need to make this width larger if we when we're considering that it's relative to the cell. So that's just an example, but those are sort of the formulas for calculating the width relative to the cell and the height. So those can be greater than 1, and oftentimes they are greater than 1. So the box coordinates, we're going to set to a torch tensor of x cell, y cell, width of cell, and the height of the cell. All right, and then the targets of this particular scale index, of this particular anchor on the scale, it's, as you can see, it gets pretty messy. But on this particular scale, on this anchor, we want to set I and j, and then 1 to 5 equal to those box coordinates. So 1 to 5 here is x, y with height. And the last thing to do is the same thing. So targets scale index of anchor on scale I, j, 1 to 5. It's going to be int of class label. And we're taking integer here because it automatically loads it as a float, but the class label should be an integer. All right. So that is it for the main part. I guess we need to also have an else if statement, and we need to make sure that so if the IOU of a particular bounding box is greater than the ignore threshold, then we want to make sure that there are so we don't punish that anchor box, so we sort of ignore it if it has a great enough IOU, right? Because we're setting one anchor box for each cell. But if there's another anchor box in the same cell that it also shares a very high IOU, then we're going to ignore it if it's higher than a particular threshold. So we're doing if not anchor taken. So we need to make sure that we haven't taken the anchor box, right? Because then we don't want to ignore it. And if it's not taken and the IOU's anchors for this particular anchor index is greater than self.ignore IOU threshold, then we want to set the targets for this particular scale index on this particular anchor ij0 to -1. And -1 here means that we're going to ignore this prediction. Okay, in the end, we're going to return the image and tuple of targets. And yeah, so that's pretty much it for the data loading. It can look pretty messy, and I noticed now that we didn't use this image size. I guess we use it in the transformations, so we don't need to have that one. As you can probably imagine, the dataset loading is actually quite expensive because it's the bounding boxes are dependent upon the image, and we also need to do the conversion of all of them dependent upon the augmentation that's been applied. And that's why we're doing this every single time and checking which cell is responsible and checking the anchors and all of that. So that's it for the dataset anyways. We're going to now move on and do the loss. So the loss, we're just going to import torch, import torch.nn as an n, and from utils we're going to import intersection over union. Okay, so we're going to do class YOLO loss, and we're going to do, I guess, YOLO loss, and then module, we're going to do init, and super init. And what we want to do first is we want to specify all the loss functions that we're going to use. So we're going to use mean squared error, and then dot mean squared error loss, and let me see. Yeah, so mean squared error here is for the box predictions. Then we're going to use BCE with logit loss. So that applies sigmoid as well. Then for our classes, in the paper, he used BCE as well, but since we only have one label per box, we're just going to use entropy. So we're going to use cross entropy loss, sort of what you normally do, right? When you do, if you train on Cypher10, ImageNet, you would use cross entropy loss to train it. And that is the case when you only have one class. Yeah, so we don't have multi-label loss here. But anyways, then we're going to do self.sigmoid is nn of sigmoid. Then we're going to have some constant signifying, there I can say it, signifying how much each loss should be valued, so to say. So we're going to have lambda class is going to be 1. We're going to have lambda no object is 10. And there's nothing magic about these values. I just wanted something that for a particular threshold to sort of make sense. And in this way, we value no objects more. And yeah, that's pretty much it. Then we're going to have lambda object, and we're going to put that to 1. And then lambda box, we're going to set that to 10 as well. So we value box and no object more. But honestly, I think you can do this and it will still work. So there's nothing, I don't think there's nothing magical about those. And those are not from the original paper. Those are just from me trying and just testing stuff. Anyways, in the forward, we're going to send in the predictions, we're going to send in a target, and we're going to send in an anchor, the anchors. So we're going to compute the loss for each of the 3 different scales. Right, so remember in the dataset, we computed targets for each of the 3 scales directly. And for the loss, we're going to compute the loss for a single scale. So we're going to call this 3 times for every forward pass. Okay, so what we want to do first, we're going to check where is there an object in this target. So we're going to do, we're going to take out the sort of binary values where there's an object and where there's not an object. And then we're going to check where there's not an object, and we're going to set that to 0. So why we're doing this is because, remember, we ignored some predictions if the IOU was greater than 0.5. So we just want to make sure that we're ignoring those, and we're just taking out the ones that are actually 1s or 0s in the target. All right, so what are the different losses that we're going to have? So we're going to have no object loss, we're going to have object loss, we're going to have box coordinate loss, we're going to have class loss, and that is it, right? So we're going to have those 4. So the no object loss is going to be self.bce of the predictions of 0 and 1 of no object. And I'm doing this to just keep the dimensions so that we index with no object. We're actually just, it's gonna not give us an error. So that's why I'm doing that. And then for the target, dot means all of them. Should probably mention that. And then we're taking out 0 and 1. This is just going to take out the 0, 1, but when we do 1 like that, it's going to keep the dimensions. So it's not going to remove the last dimension, which would give us an error when we're looking for no object, which is this binary tensor right there. So we're just computing no object loss with BC loss like that. Okay, so for the object loss, we need to first get the anchors. No, sorry, for the object loss, right. So what he did for the object loss is not just use ones, at least not from what I understand. So my interpretation of the paper is that we're gonna set it equal to IOU. So the object score that the cell is going to, the cell is going to say, here's the probability that there's a box in this cell. And that is going to correspond to the IOU that it believes the prediction is. So for that, we need to actually compute sort of the target at that particular time. So we're going to first do anchors.reshape 13112. And the reason for this is we wanted to match, so this is a little bit tricky, I guess, but we wanted to match. So in the beginning, when we send in the anchors, they're going to be 3 by 2, right? So we're sending it in for a specific scale. We have 3 anchors for that particular scale, and each anchor has a height and the width. And we then want to reshape it like this, just to match the dimensions of the height and the width that we're going to multiply. Remember the formulas that we looked at? We're going to multiply, I guess, PW times exponent of TW. TW is what comes out from the network. We're going to take exponent and we're going to multiply by PW. To multiply this for all the examples and all the different scales, for all the anchors and all the different cells, right? Those are that dimension. We need to reshape it like this, and then we'll utilize broadcasting to do it for all the different cells. So the box predictions are going to be torch cat of self.sigmoid of predictions of 1 to 3. So we use sigmoid on the height of the x and y coordinates because we want them to be between 0 and 1. And then for the other ones, we're going to do torch.exponent of predictions 3, 5 width and height, and then we want to multiply that with anchors, and we want to concatenate along -1 dimension like that. The IOUs we're going to calculate with intersection over union, and we're going to and I've covered that exact function in the previous video. So box preds of object and then target of 1 to 5 of object. So we're computing the box predictions for the ones that alright, so here I just noticed an error. We need to make sure that we do torch exp of that and then times the anchors. And I also noticed one other thing is that we compute the box predictions, or we concatenate them, and then we want to take out the ones that there's just an object in. So we would do it that way. And then one thing I did also is I wanted to do dot detach. So I don't want there to be some weird gradient going changing the box prediction dependent on the IOU. I want the model to be able to just see the bounding box prediction that it did, and then output what the IOU should be for that particular one. But I'm not actually entirely sure about this. It could probably work even if you remove this dot detach, but I felt it was safer to just do dot detach, make sure that it doesn't impact the computational graph in some weird way. But yeah, anyways, so then for the object loss, we're going to do self.bce of predictions. We're going to take out the object, so the cells and anchors where there's actually an object dependent upon in the data set which we set to 1. For the targets, we're going to do IOUs times the target of where there's actually an object. So remember, all the work that we did here is just to multiply with the IOUs, and that is to say that every object score should not be just set to 1 if it believes it's an object. It should be more nuanced and say, yeah, there's an object here with a particular, so the IOU of the particular anchor that particular outbounding box that was predicted. So it wants to tell us sort of this is what we believe the IOU is with the true sort of bounding box for that particular object. So going to be IOUs times that, and hopefully that makes sense. That's my interpretation of how they did it in the paper. Now for the box coordinates, what we're going to do is we want to do it, so we want to do similar as we did here, right? We want to do self-sigmoid of the predictions between 0 and 1, so x and y, and we want to do torch x of the predictions times the anchors. But what they actually did in the paper, just to have better gradient flow, is that they changed the targets instead of the predictions. So they did predictions of 1 to 3, and they did self.sigmoid of predictions 1 to 3. And then, so these are the x and y to be between 0 and 1. For the target, what they did is that they just changed the width and the height by doing sort of the inverse of this. So they did torch.log of the target of 3 to 5, and then divide that by anchors. So as you can see, exponent is the sort of the opposite, right, of exponent. So log is inverse of exponent, and then we divide by anchors. One thing I also did is I added 1e minus 6 just to make sure that we didn't have any sort of a weird torch log of 0. But yeah, this is just for better gradient flow than using this. So that's the only thing here. And then for the actual box loss, we're going to use mean squared error between the predictions of the particular xy width and height, and we're going to take out where there is an object, and target of 1 to 5 where there is an object, right? So we just modified the target here instead of modifying the predictions to have better gradient flow. Okay, so the class loss is the only thing left, and that is going to be pretty simple. It's just going to be predictions of 5 and forward, all the nodes from that point where there is an object. Right, we don't want to predict classes where there's no object. And similarly for the target, we're gonna do 5 of object, and we're gonna do dot long. So that's it. So I guess what we're doing here is we're just taking out the class label associated with that. So, you know, cross entropy works that you send in all the logits as the input, and you send in which node is the correct one, or which class is the correct one. And then we want to, at the end, we want to add all of those together, and that's our loss. So lambda box times box loss, right? We're changing the, depending on the constants that we set in the beginning. Then we do self.lambda object times the object loss. Then we do self lambda no object times no object loss. And then we do self lambda class times class loss. Whew. All right, that's the loss function. And also, I guess this is just for a particular scale. So in the forward part, when we in our training function that we're going to create, we're going to have to put that sort of add all of those for all the scales, but we'll get to that. So this is computing the loss for a single scale. Okay, now that we've done the model, we've done the data set, we've done the loss, we've done the most tricky parts, we're going to create a config file. And the config file I'm going to copy paste in, and I'm gonna show you what it looks like. So the config file is just the hyperparameters, right? So we're specifying which data set that we want to use. We're going to set Pascal VOC, device CUDA. Here I've created in a utils, I've created a seed everything function. If you want deterministic behavior, you can, I guess we can just remove that for now. And we can do num workers, batch size, image size, num classes. This should be 20 for Pascal VOC. Learning rate, maybe we can do 1e minus 4, weight decay, num epochs. We have a confidence threshold. The confidence threshold is so if the probability of an object is greater than 0.6, then we say that there's an object in that one, so that we pick out those ones. To calculate the mean average precision, we use an IOU threshold of 0.5. To remove bounding boxes in non-max suppression, we use 0.45. Then for S, we use, so this is just going to be, 13, 26, 52, as we've seen previously, but just more general. Pin memory, load model, save model. Maybe we can do false on this right now, and false maybe. Then the checkpoint file, where it's going to save the model, and this is just basic Pytorch stuff. It's in the utils file, just save and load model. The image directory, it's going to be the dataset plus images. That's just the structure that we looked at for the dataset. Here we also have the anchors. And so for the first scale, we can see that the width and the height are quite large. For the middle scale, we can see that they're smaller. And for the last scale, we can see that they're a lot smaller. So those are just for the anchors that was computed with k-means algorithm on the MSCOCO dataset. So what you would do if you're using a completely different sort of dataset is you would probably want to do that. But I think those anchors are pretty general, and I think they would work on a lot of different data sets. All right, for the transforms, we're using albumentations, and we're doing a.compose. And what we're doing here is, instead of doing just a.resize to 416, what they did in YOLOv3 is they kept the aspect ratio of the image, and they just padded sort of the top or the sort of the sides of the image with just a constant value. So that's what we're doing here. And then we're doing a random crop instead, and we're also specifying that the scale should be 1.2, so that the image here is larger than what we're cropping. So we're cropping different parts of the image. Then we're doing random crop, color jitter, and then we're also doing a shift scale rotate. So we're rotating the image, and we're also doing shearing, but we're taking one of those two. Horizontal flip, blur. I'm not really sure what these are, to be honest. I just put them in there. They looked all right, but we're blurring the image. We're using this posterize. We're sometimes converting it to a gray image. We're sometimes shuffling the channels, and that's pretty much it. And then we're specifying that they are in YOLO format, and that the min visibility means that basically when we do the augmentation, the box shouldn't just remove, or rather, if we do an augmentation and the object is removed so that the original bounding box is just shown with a 40% ratio of what it was originally, then we remove that bounding box. Yeah, and then for the test transform, we do pretty much the same thing, but we remove the augmentation. And then we have all the classes of Pascal, and then we have all the classes of Coco. That's, yeah. So that's it for the config file. Nothing, we didn't really do anything here. Just write all the stuff that might impact the model here. And then instead of changing all the different functions or different files, just changing the config file. All right, so let's do now the train function, right? That's the last part. And, one thing that you probably should do as well is you should probably test each of these parts independently to make sure that they work. I'm just hoping that I wrote this stuff correctly now, which is not a good thing, but yeah. All right, so I'm gonna copy paste in the imports. We're gonna use the config that we just created, torch, optim, YOLOv3 from the model, TQDM for progress bar, and then from utils, we're going to import mean average precision. I have a video on that. We're importing another function, cells to boxes, which is just to convert the cells, right? We're getting an output for each of the cells, and it converts it to actual bounding boxes relative to the entire image. And that is because we want it in that format when we're computing, MAP, non-max suppression, and also when we're plotting a couple of examples. So this isn't too difficult. It's going to be on GitHub, but I don't want to go through it because it's a little bit messy. But yeah, cells to boxes, get evaluation boxes is it's just associated with mean average precision. So we want to get all the predicted boxes and all the targets. None of this is really essential to YOLO. This is just sort of the steps in between to evaluate the model and all of that stuff. We have save checkpoint, load checkpoint, check class accuracy. Sometimes we check the accuracy. We have another get loaders, and that one I might just show you. So in the utils file, if we go down, get loaders, all it's going to do, it's going to take in the CSV path, and it's going to import YOLO dataset. It's going to create a train dataset, test dataset with the particular configurations, and then create train loader and test loader and train eval dataset, train eval loader as well. So this is just making it not as ugly in the train function. But this is nothing difficult. We're just calling the YOLO dataset with the initial values, and then we're doing a train loader with the specific configuration that we set. And that's pretty much it. So yeah, let's go to the train function now, and let's implement this. And this right here is just so that we get some performance improvements. All right. So we're going to do train function. Let's just do the structure right now. But the structure is just going to be a main function where we set everything up, and then we run the train function, and it's going to train one epoch. And then we're going to do if name equals main. We're going to run the main function. So that's it. Maybe we can do the train function first. So we're going to take as input some train loader, some model, some optimizer, what else? Some loss function. We're also going to take in a scalar, and that is because we're going to train it in float 16 so that we can have some performance improvements and some, essentially double the VRAM. Then we want to have the scaled anchors. We're not going to use a scheduler, so let's just do it like that. Then we're going to do loop is TQDM of train loader. We're going to do leave equals true. So this is just to get a progress bar. Then we're going to do losses. We're going to sort of store the mean loss of every epoch so that we can see it in a nice way. So what we want to do is we want to go through for each batch and the X and Y in enumerate of loop. All right, so then what we want to do is we want to make sure that everything is in the correct device. So we do that by doing x.to config.device, right? So we have everything in the config file. Then you do y0, y1, y2 is y0.to config.device. And so what's going on here is that we have 3 different scales, and we have a label for each of the scales. So we're getting out all of the ones. And so we're getting y1.to config.device, y2.to config.device, and that's the making it to CUDA. Then we're going to do .torch CUDA.amp.autocast, and so this is just float 16 in Pytorch. I've also made a video on this. So we're doing it inside this, and it's going to automatically keep track of float, sort of what should be in float 16. So we're doing out of model of X. Then we're computing the loss, which is going to be loss function of out of 0 and y0, and then scaled anchors of 0. So when we're sending in the scaled anchors, we're doing that because they're going to be dependent on the cell size that you use for the image, right? So the in the config, I wrote down anchors right here that are copy pasted from the paper, but these are in the entire image. So the width and height dependent on the entire image. Well, we want to have them as dependent on the specific cell. We want to scale them appropriately dependent upon the cell size. So we just do it. We're going to do it in the main function, but just to let you know, that's the scaled anchors. Then we want to add. So let's see. We want to do like that. Then we want to do the same thing pretty much, but we want to do it for y. So out of 1, y of 1, scaled anchors of 1, and then plus loss function of out of 2, y2, scaled anchors of 2. And that's it. Then, all right, so then we want to append this to losses. So we're going to append loss.item. We're going to do optimizer.0grad, scalar.scale of loss.backward, then scalar.step of optimizer, and also scalar.update. So that's, you know, pretty similar to loss backward, optimizer step. You just have to do these instead. And then we want to update the progress bar. So we're going to compute the mean loss, which is the sum of the losses divided by the length of the losses. And then we're going to do loop.set postfix, where loss is equal to mean loss. So in the progress bar, we're keeping track of the mean loss all the time. And that's it. So that's what we're doing in the train function. Now for the actual main function, we're going to get our model, which is YOLOv3, the one we did. We're going to set num classes equals config.num classes. And then we're going to do .to config.device. The optimizer is just going to be optim.atom of model.parameters. Learn rate is going to be config.learning_rate. Weight decay is going to be config.weightDecay. And then we're going to get the train loader, test loader, and then we're going to get train eval loader of get loaders. So this is just a train loader with augmentation. Test is just test data set with no augmentation. Train eval loader is just a train data set with no augmentation. So this is just if you want to make sure that it's not overfitting and all of that stuff. But we're not going to use that now. So I could remove it, I guess. But we could keep it there. It doesn't matter too much. So train CSV is config.dataset plus train.csv. And then test CSV path is config.dataset plus train test.csv. And that's it. Now we want to check also if config.load model, then we're just gonna load checkpoint of config.checkpoint file, model, optimizer, and then we're gonna send in the learning rate as well. So for the scaled anchors now, we're gonna do them so that they're a tensor. So towards that tensor of config.anchors. So we're just making all the anchors to tensor. Then we want to scale them. So we're scaling them towards that tensor of config.s. And then we're doing unsqueeze 1, unsqueeze 2, and then .repeat 1, 3, 2. So the reason why we're doing this is just so that we can do the multiplication. So yeah, we're unsqueezing it to make sure that it has the same number of dimensions as the anchors, and then we're multiplying. So all the anchors in scale 1 should be multiplied with that particular value of s 0. So for example, we have 3 anchors. Maybe I should go to the config file. In the anchors here, all of these are for scale 1. We want to multiply all of these with the value of s that is particular for that scale, and similarly for this, and similarly for this. And to make it possible to multiply all at the same time, we're just doing this right here. And then at the end, we want to make sure that it's on the correct device. So .to_config.device, and that is it. So now we're just gonna set up the training part. So we're gonna do for epoch in range of config.num epochs, and we're gonna call the train function of the train loader, of the model, of the optimizer, of the logs function, the scaler, and the scaled anchors. Maybe I missed something here. So scaled anchors, and that's it. But we haven't specified the loss function. So the loss function is just YOLO loss. And then the scaler is going to be torch.cuda.amp.grad scaler. So we're sending those in right there. And we're also going to send in the scaled anchors. Okay, so we're running it one epoch. This is one epoch. Then we're doing if config.save model. We're doing save checkpoint of model optimizer, and that's it. And then maybe we can also do so I'm gonna copy paste this in because this is not really this is just a utils file. So all we're doing at every 10th epoch, we're running a check class accuracy on the test loader. We're also running get evaluation boxes. So we get prediction boxes, true boxes, and then we're running the mean average precision. So we're just checking what's the MAP value on every 10th epoch. You could check out those specific ones, but that's not, this is just to make sure that our implementation is actually correct and to evaluate our model. Okay, we've written a lot of code, like so much code. So let's just take 8 examples, and then we'll take 8 examples for the train and the test function, and maybe we'll just train on the test loader because we don't want to. Maybe it will be too difficult with all the augmentation. So we'll just use the test loader and make sure that we can overfit on that with minimal augmentation. And in the config file, we can also remove the weight decay, so no regularization. And yeah, I'm expecting to get errors now. So let's run it and let's see all the mistakes I've made. All right, so we need to go back to ndim, which is right there in the dataset file. Yeah, this should be nd min. So the number of minimum dimensions is going to be 2. So even if we just have a single bounding box, it should just still be 2 dimensions. All right, let's see the next one. All right, so this is in the loss function. So we're doing something wrong with no object loss. Right, so we need to do parentheses right there, and we need to do parentheses right there. Then we need to remove that one. Right, this is the input of the predictions, and these are the targets. All right, let's see the next one. All right, so I think the next one here is that we're taking out the objects, right, where there's actually an object, and we need to do the same thing for the target. So we're just going to take out the ones that there's actually an object in. All right, so I've debugged quite a bit, and one thing is that let's change the number of examples to 100. I think it still works for 8, but using 100 we can make sure that it actually works. And sometimes I've encountered issues with batch norm using very low, using a single batch. So let's use 100, and then in the data set, one large mistake here is that we're resetting this to be class label, but we should only be sort of the 5th index should be class label. right? Otherwise we're overwriting, otherwise box coordinates will be overwritten with the class label. And then another mistake is that after we've taken this box, we need to make sure that we've actually set it to be taken for this scale index. So we're looking at an anchor for a specific scale, and after we've taken an anchor, we want to do has anchor of scale index equals to be true. So that's another thing. And in the config file, I've changed the learning rate to the Kirkpatrick constant, of course, 3e minus 4, and that's pretty much it. I think I also changed the confidence threshold to 0.4. All right, so now let's run it and make sure that this actually works. All right, so I ran it for, this is, I guess, 20 epochs, and we can see that we got class accuracy 70%, 99, 27, map got to 0.5, and then after 20 additional ones, we got 99% MAP, and I stopped it there. Yeah, I'm gonna release a pre-trained weight on Pascal VOC that has about 78 MAP on test, and MSCOCO I'm currently training, but it has around 42 MAP, so it still has a bit to go. One thing that I think could also raise the accuracy, which we didn't implement, is multi-scale training that he did in the YOLOv2 and YOLOv3 paper, meaning we're training on different scales. So maybe we could change this 416 to 608 and other image sizes. So that's one thing you can definitely do to improve it. But yeah, that's it for YOLOv3 from scratch. I'm gonna upload everything to GitHub, and it's gonna be in the description. But thank you so much for watching the video, and I hope to see you in the next one.